let's get right into it. What we've done here is we've looked at ways of encoding discrete variables. And what do I mean by discrete variables? I mean specifically variables that are higher than binary. And these come up a lot in real-world situations. Think of a real optimization problem. If a truck can go down any of 3 roads, a task can be scheduled at any of 5 times, component can be placed any of 7 places on a chip, etc., etc. So this is something that you might run into very naturally in the real world. This isn't some abstract mathematical construction, but it's going to be, or can be, really important to have to deal with. Sorry, I believe some of the summation symbols that were supposed to be there may have disappeared, but that should be a sum over those indices. But the way we define this is a discrete quadratic model, which means we think of these terms that can take multiple values and they're multiplied together pairwise. And this can define a lot of problems, anything where sort of 2 things can interfere. And we'll think of different ways to encode this. I'll talk about what's called a domain wall encoding, which I've presented in previous work. But what I did in this work is we really looked into, me and my colleagues, we really looked into how this works and where it gives you advantages. And we found that not only does this encoding sort of help put this on the chip more efficiently, it also helps the physics. So if we're thinking of going discrete variables, putting them into a binary encoding, the first thing you might think to do is assign each one a bit string. That's obvious. The problem is on a D-Wave device, and realistically most devices, you'll only have quadratic interactions. And when you try to do that, it becomes kind of terrible. Things sort of add up. There's the traditional method, which is called one-hot, where basically you constrain a group of variables and you say only one's allowed to be 1, say 3 variables, one's allowed to be 1, all the other ones have to be 0. Automatically encodes a discrete variable. And the method here, which I'm not going to go through all the details of, is called domain wall. You encode it as a sort of break in a chain. If you want the details of how the actual encoding works, there's all kinds of great stuff on here. There's actually a blog I wrote for QCI not too long ago on this. It explains it in less technical terms, but those are the papers to look at. And also one that just shows how it works on a problem. So there are still some important questions that we cover in this work. First off, they're very efficient for arbitrary interactions, but what we've shown here is that you actually can't do any better. And that if you want arbitrary interactions for anything that's an interesting problem size, you actually might not as well even try to look for anything better. Not some magic like other new trick that you could do beyond what we have that could get even more efficient. Because what we found is that this domain wall encoding is more efficient than the traditional one-hot. By construction, basically, you get 1 fewer variable the way you do this by encoding it as a slice on a chain rather than as a group where you've constrained one of them to be 1. And then we also showed experimentally that the dynamics actually are more favorable in a very concrete way in that it freezes later, and I'll explain what that means later on. And that builds on the previous work, which showed it works better and showed it's more efficient. Although that's showing it's more efficient is fairly trivial. You just count the qubits. But what we showed is that beyond that, it's what we show here. It's the most efficient you can get. If you and we looked at multiple cases. We looked at, well, what if you say take a binary encoding and you say, well, okay, if I do that and I try to count the interactions, I don't have actually enough to with just quadratic interactions, so just pairwise interaction with the qubits. If you count them up, you don't have enough. However, at least for large sizes. However, when you look at this, You could say, well, maybe I use some gadgets and use some auxiliaries, and here we did the counting. We showed, no, that's always a losing proposition, at least for anything that's bigger than sort of a 3-variable problem, which isn't actually going to be interesting in the real world. The way we did this is we looked at sort of a critical degree, and said, okay, well, what's the degree of a graph we could have where this could where this wins? Because if you're adding auxiliary variables, you have to add them per interaction. So how many interactions can you get away with per qubit? And it turns out this becomes really small. It's 1.4. Even if you just have a line, that's degree 2. So basically we've shown that this it's the best you can do. No, there's no other trick you could do to get a more efficient. Best in terms of number of qubits. You can't squeeze this into more qubits if you want arbitrary interactions and if you only have pairwise interactions between the qubits. What we've then looked at for our experiments is we looked at an important problem known as the quadratic assignment problem. And what this problem is a version, you can either think of it as coloring a complete graph or as matching facilities to locations. And basically what you have to do is you have to uniquely match them. Now, a weighted version of this is a hard problem. We actually looked at the unweighted version. So we looked at just, can you match these? So this is actually a trivially easy problem to do, but it allows us to experimentally test things, and we don't need to worry about the complications of having a hard problem on top of this. It has an m factorial full degenerate ground state, where m is the number of elements, locations, and facilities you're matching. So we do some experimental test on an advantage in either, and what we're looking for here is comparing domain wall to the traditional one-hot method. And so you can see what we found at small sizes. When we run quite a lot of runs, both methods just find all the possibilities, all the feasible solutions. As we get to bigger and bigger sizes, that doesn't happen anymore. And we can see the domain wall falls off slower. It's doing better. This is possibly not very surprising given the previous work. And following from that, we can look at the rate of feasible solutions. And again, there's more feasible solutions, at least at large sizes, when we're using this better encoding. That's consistent with work that's been done before. We also see an interesting crossover where actually at small sizes, you're slightly better off doing one hot, but those aren't really interesting problems in the real world. You're interested in solving large optimization problems, not tiny ones. The tiny ones you can just solve by exhaustively searching. If we think about how we're getting this shape, why we're getting this crossover, one answer might be, oh, well, maybe if we can just think of this as a system undergoing thermal excitations and that it's just sort of frozen somewhere. And we can do this, and we can do some sort of classical Monte Carlo sampling, and we indeed find the same crossover behavior. We don't find it at the same spot, but that's already pretty good. We've sort of qualitatively shown one of the features. This is building up to something, an important result with the why the encoding's better, but we kind of have to go through some of the details of understanding it first. So then these problems involve a highly connected graph, so they minor embedded. So one question is, okay, which actually needs stronger chains if we use the uniform torque compensation method, the default method for minor embedding. And we actually find something interesting. Even though the domain wall was doing better, it's actually using stronger minor embedding chains. So that means it's actually squeezing the energy range of the problem more. And we didn't investigate if we could use other methods to determine the chain strength. Possibly if you used another method, you could get away with weaker ones for domain wall. We haven't really looked at that thoroughly, but using this method, the chains are stronger, but you're still actually doing better. We can think about why that is. And again, here's a thermal equilibrium model where we look at, well, what happens if we just have it fixed at a temperature? And what we find is, as we raise the size, we get, again, the same crossover. And if we think about what's going on at this large size, this kind of makes sense. So one thing I mentioned before was in the domain wall encoding, you're using one fewer qubit per variable. So what that means is if you're thinking in terms of entropy, what you're actually going to have is you're going to have a larger space. There's more things that can go wrong in the one-hot encoding. And so what that means, and the difference is going to grow exponentially as you're adding qubits. Every time you add a qubit, the one-hot, the space is becoming twice as big relative to the domain wall. So what you can kind of argue that as you go to very large sizes and high temperatures, which again, you're raising the embedding strength, and effectively it'll probably freeze earlier too in the anneal. I'll get to what that means later on. What you end up having is you end up having an effect where there you'd expect it to be doing something close to almost guessing. And if you're guessing in a smaller space, there's the same number of correct answers. You're more likely to hit the right answer with the domain wall. So this is something that I think isn't usually considered when you think about how you've encoded your problem and what the size is these thermal effects really care what the size is because there's more ways to be wrong. And you want fewer ways to be wrong. And so if you can encode a problem that's smaller, not only is it more efficient to embed, there's fewer ways it can go wrong. So we've looked at this. Now let's actually take our data and take this, what we've had here, these probabilities of having a feasible solution, and let's use these to actually estimate some of the energy scales, estimate what the annealer's doing when it's run and when it's sort of finally turning off. So we'll do a very simple thing physicists like to do. We'll assume a frozen-in thermal distribution. This is like the Kibble-Zarek approximation if you're a physics fan. And we assume and there's a known physical temperature of the device. This is fairly well established. And we've just measured experimentally the success probability. So from this, if we're given the annealing schedules, which are provided by D-Wave, we can back calculate the energy scale B, so on this annealing schedule, B is the strength of the problem term. So that's how strong the couplers are that define your problem. T is the strength of the transverse field, and T is just the temperature that stays constant. So we can back calculate that energy scale, and therefore we can calculate this sort of derived quantity S and ask, where have we frozen? And we can compare the two, and we can really say, okay, if we're running this under the two encodings, are they more or less freezing at the same time? Are they freezing differently? Is the actual physics that's going on different using a different encoding? And this is a way of thinking about it people don't usually do. People usually think, okay, encoding, that's a computer science thing. You want to make your encoding as efficient as possible, but you don't need to think about what the chip's doing with your encoding. Turns out, and then we have to, at the end, go back and verify that what we did was sensible, because we're using a thermal model. We're not including the quantum fluctuations. We have to make sure that was actually an okay thing to do. It's a boring thing, but otherwise your work could be nonsense. What we can do is for the two two devices, we can say effectively what is the temperature. And what we mean here is, assuming it's a thermal distribution using this simple model I talked about before, let's back calculate what the temperature would have to be to get that success probability. We can do that for temperature over maximum coupling. We can also calculate this S parameter, where does it freeze? And what we found is that you're freezing effectively later with the domain wall encoding. So your physics is working better if you're using a more clever encoding. And I'll talk about why that might be later on. It has to do with the way you update something encoded as a break in a chain, as a domain wall, versus something encoded as a value of a qubit within a constraint, a value of a qubit within a constraint group. It has to do kind of with the number that you flip. And so, yeah, this is a really important point to, and sort of the main point of what we're doing, or at least one of the main points. The first was that this is the most optimal you can get. You're not going to find a more efficient encoding in the sort of computer's way of thinking about it. How many qubits do you have per or how many binary variables do you have per discrete variable? But then there's also how's the physics of the device doing. And here we see that this temperature, which is sort of a proxy for how well are the dynamics going through and solving the problem. So to understand why this might be, we have to go back and think about the encodings. So I'll go through how these work. But early on, I kind of just mentioned this domain wall encoding and didn't say how it works. Let's actually think about how the one-hot and domain wall encoding works. The one-hot encoding, what you do is you balance interactions that want the qubits to be, or the variables to take different values, binary variables. They could comprise multiple qubits. That's why I don't call them qubits. And you balance that off with single body terms, with fields. And if you look and you say you want to update this, what you have to do is you either have to go through a 2-hot state where you have 2 of them are 1, or a 0-hot state where none of them are 1, and then flip back into a valid state. So you have to pass through an invalid state to get to a valid state. So the domain wall encoding, I didn't really explain how this works before. What you do is you have a chain, ferromagnetic spin chain, meaning all the variables want to be the same. You constrain the 2 ends. You can either break the constraints at the end or break a constraint in the middle. It involves 1 fewer qubit. And crucially, when you flip one of these, you only have to flip a single binary variable. And so the underlying physics makes the dynamics more efficient. And we're near the end. We showed our model was justified. I'm not going to go through that. That's just basically looking at the scales, and we could ignore the quantum effects. And yeah, this is just summarizing what I said before. I see I'm out of time. Thank you, and goodbye.